Okay, let's unpack this. When you hear the name Einstein, what immediately springs to mind? For most of us, I think it's, a flash of genius, that iconic wild shock of hair, maybe EMCFR. He's quite literally the universal synonym for genius, right?
Absolutely. The name itself just screams intelligence.
Yeah. What if we told you that the path to becoming the Albert Einstein wasn't this smooth, inevitable climb,
Mm.
that it was actually a winding road filled with surprising rebellion, moments of pretty profound rejection, honestly, and this deep, quiet curiosity that, well, for a long time went almost entirely unnoticed by the academic world.
Yeah, and what's truly fascinating here, I think, is that our deep dive today isn't just going to be a list of his achievements. We all know he achieved incredible things.
Yeah.
Instead, we're tracing the evolution of a mind that constantly challenged the very fabric of accepted wisdom.
Yeah.
We're aiming to show you, drawing from sources like Albert Einstein, A Life of Genius and Discovery, how this seemingly ordinary boy, I mean, he was often seen as different, even slow, how he ultimately reshaped our fundamental perception of reality. It's really an exploration of not just what he discovered, but who he was, and why his particular way of thinking led to such monumental shifts in how we understand the universe.
So you're going to hear about this surprisingly simple gift that apparently ignited his lifelong obsession with the unseen forces of the world. You'll hear about the quite significant struggles he faced in traditional schooling. I mean, things that would have derailed a lot of people.
Oh, definitely.
And how one truly incredible year, 1905, spent largely in isolation, just changed absolutely everything for physics and for him personally. We'll also delve into the profound, complex ethical dilemmas his groundbreaking work inadvertently created later on. That's a heavy part of the story.
It really is.
And the enduring legacy, of a man who consistently valued imagination and independent thought above pretty much everything else.
Yeah.
So prepare for some genuine aha moments, because there are just so many unexpected details waiting for you in this material, things that might make you rethink what you thought you knew about this scientific icon.
It's a journey that really underscores something important, I think. That the most profound breakthroughs often emerge not from conformity, not from fitting in, but from individuals willing to question every assumption, to look beyond what's accepted and to ask the most fundamental, sometimes really uncomfortable questions, even when doing that makes you seem like an outsider.
Okay, so let's dive right in. Let's go back to the very beginning, the genesis, you could say, of this extraordinary mind. Albert Einstein was born March 14th, 1879, in Ulm, Germany. Now, when we picture a budding genius, you often think of, like, a child prodigy, right? And speaking complex sentences super early.
Yeah, the myth of the instant genius. Right?
Exactly. But the reality for young Albert, according to our sources, was actually quite different, very different from that myth. He did speak as a child eventually, but apparently very, very slowly. So slowly, in fact, that his parents, Herman and Pauline, they actually worried he might have a learning disability or some kind of developmental delay.
Right, you can imagine their concern.
Yeah. He apparently didn't speak fluently until he was around 3 years old, which, when you think about the man he became, that detail is pretty surprising.
It truly is an arresting detail, isn't it? And it humanizes him in such a profound way. It takes him off that pedestal a little bit. What's fascinating here, though, is how this perceived slowness in early speech, well, it might have actually served as this unexpected crucible for his unique intellectual development.
How so?
Well, think about it. While other kids were rapidly verbalizing, interacting, learning through that immediate back and forth, Einstein, during those really formative years, might have been just quietly observing, processing, building these intricate internal models of the world in his head.
Okay, so less outward communication, more inward processing.
Exactly. Imagine a child for whom talking is just a slower process. Maybe that leads to a greater reliance on visual thinking, on conceptual thought. It could have fostered this deep internal reflection, allowing him to ponder things, question things in silence without the pressure of having to articulate it immediately.
Interesting.
This period might have actually cemented his unique perspective, a mind that wasn't about, rapid-fire answers, but a much deeper, more contemplative and fundamentally independent way of thinking. His genius, maybe, wasn't about quickness, but about profound, sustained questioning.
And that quiet, curious nature, that sort of unique way of processing the world, it didn't take long to show itself in a really significant way. Our sources point to this single pivotal moment. He was just 5 years old, apparently quite sick in bed. And his father gave him a simple compass. Now, for most kids, a compass is what? A toy, maybe a neat little gadget.
Right, points north. Big deal.
But for young Albert, it was like an existential question handed to him in this small brass casing. He looked at that needle, always pointing north, no matter how he turned the case, and he was just utterly transfixed.
Yeah?
And he asked this question: what invisible force moves the needle?
Wow. At 5 years old.
Right. It wasn't just a kid's fleeting wonder. It was the absolute essence of scientific inquiry. That drive to understand the unseen forces governing our world.
It really was. And stepping back for a moment, that simple question about an invisible force, it perfectly prefigures the entire trajectory of his later work, doesn't it? I
Yeah.
mean, his whole career was about fundamental unseen forces governing the universe.
Like gravity.
Exactly. Think about general relativity. It fundamentally redefined how we understand the invisible force of gravity. He showed it wasn't a force in the traditional sense at all, but the curvature of space-time itself.
Right. Mind-bending stuff.
And his work on the photoelectric effect, the thing that actually won him the Nobel Prize,
Yeah.
that laid the groundwork for understanding the electromagnetic force through light, quanta, photons.
Does that compass?
Yeah.
It wasn't just about magnetism for him.
No, it was about the mystery, the underlying mechanisms of reality, the recognition that there's so much more to the world than what we can directly see. That became the driving intellectual question for his entire career, you could argue. It really speaks to a mind that was never content with just surface observations. He was always digging for the deeper, hidden truths, the elegant simplicity beneath the complexity. That was the seed right there.
So, okay, you have this incredibly curious, internally focused kid, already pondering invisible forces, seeing huge questions in simple objects. And then he enters the school system, specifically the rigid, traditional Prussian system of the time.
Oh boy. Yeah.
And as you might guess, it was, well, not a great fit.
Understatement of the century, probably.
Our sources paint a really clear picture. He just wasn't a fan of this rigid schooling. It was all about memorization, rote learning, strict discipline.
Not exactly fertile ground for imagination.
Not at all. Not for critical thinking or individual exploration. And
Yeah.
his teachers, predictably, they found him defiant.
Saw him as difficult.
Yeah, a disruptive influence, often daydreaming, apparently, or questioning authority instead of just passively soaking up the facts. It paints this picture of a mind that just refused to be boxed in.
It really highlights a critical conflict, doesn't it?
Yeah.
You've got this inherently creative, questioning, imaginative mind slamming up against a system designed for conformity, for churning out obedient citizens, essentially.
Right.
His defiance, it probably wasn't just rebellion for rebellion's sake. It sounds like it was a profound demand for intellectual freedom, an insistence on understanding why things worked,
Yeah.
not just memorizing how.
And while the school system saw him as difficult, maybe even a bit of a lost cause.
At home, it was a totally different story. He was independently devouring knowledge, just soaking it up.
Our sources say by the age of 12, he'd already taught himself calculus, algebra, geometry.
Which is just staggering.
It really is. And he wasn't just memorizing formulas. He was apparently grappling with the big concepts, light, gravity, time on his own terms, driven purely by that insatiable curiosity we talked about.
Yeah. And this stark contrast,
Yeah.
Defiant, maybe underperforming in school, but this dreamer, this self-taught master at home. It underscores a powerful truth, doesn't it?
What's that?
That true learning, especially for a mind like Einstein's, often blossoms most vibrantly outside the traditional structured environments.
Yeah, that makes sense.
It suggests that sometimes the very institutions we create to foster learning can actually inadvertently stifle true genius if they don't allow for that intellectual autonomy, that curiosity, that independent exploration.
So this clash with the system, this fundamental mismatch, it only got worse as he got older, right?
It seems so. It built up.
To the point where at just 15 years old,
Mm.
think about that, 15, Einstein made this incredibly bold, pretty unconventional move for a teenager back then. He dropped out of school entirely.
Wow. Just walked away.
Yeah. And then he moved to Switzerland, specifically because their education system was known for being more liberal, more open, less rigid than the Prussian one he couldn't stand.
That's fascinating. So it wasn't just running away, it was running towards something.
Exactly. It sounds like this immediate, deliberate search for intellectual freedom. To make that kind of decision at 15, it really speaks volumes about his conviction, his need for a different environment.
It absolutely does. That decision to drop out and actively seek out a country with a more liberal education system, it just screams about his profound, innate need for autonomy and learning. The Swiss system, especially at places like the Swiss Federal Polytechnic Institute in Zurich, which he eventually attended.
Right, the ETH Zurich. Still famous today.
Exactly. It offered way more flexibility, a greater emphasis on understanding concepts, not just facts. And maybe most importantly, more room for individual inquiry, for independent thought.
So for Einstein, it wasn't just escaping something bad.
No, it was actively seeking out a place where his mind could actually flourish on its own terms, where he could follow his own intellectual passions, not just some prescribed curriculum somebody else decided was important.
That kind of self-directed pursuit.
It's the hallmark of truly deep, meaningful learning, isn't it? Especially when you're talking about groundbreaking scientific discovery. You need that freedom.
But okay, even in this supposedly more accommodating environment in Zurich at the Polytechnic, our sources highlight something really interesting. He still didn't quite fit the mold perfectly.
So it wasn't all smooth sailing even there?
Apparently not. He continued to clash with professors sometimes, often found their lectures uninspiring or maybe irrelevant to the deeper stuff he was wrestling with in his own head.
Okay.
He frequently skipped classes, chose instead to study only what genuinely captivated his imagination, what fueled his own developing theories.
Sounds very Einstein, actually, following his own muse.
Totally. But what was the consequence of this, highly unconventional approach? When he finally graduated, he had virtually no job offers.
Seriously, after graduating from the Polytechnic?
Seriously, no university wanted to take a chance on him. No prestigious lab would hire him.
That's almost unbelievable.
It is. The future icon of genius, the guy whose name would literally mean brilliant, struggling that hard just to find any place in the academic or research world.
It is incredibly surprising and honestly a bit sobering when you think about it with hindsight. This really puts into context the bigger societal challenge of recognizing unconventional genius, doesn't it?
How do you mean?
Well, we often have these very clear pathways, these expectations for academic success, right?
Right.
Excel in everything, conform to the teaching styles, network diligently, play the game.
Yeah, tick all the boxes.
Exactly. And Einstein just didn't tick those boxes. His brilliance wasn't expressed in a way that those traditional institutions were set up to immediately identify or reward at that point.
Because he skipped classes and only studied what he wanted.
Right. Which, while it ultimately led to the biggest breakthroughs in modern physics, made him look uncooperative, maybe undisciplined, in that conventional academic setting. It really underscores this profound idea that sometimes the most original thinkers, the real game changers, they don't fit neatly into the established pipelines. And that early lack of recognition, it isn't necessarily a sign of lack of talent. Maybe it's more about a lack of flexibility within the institutions themselves.
Makes you wonder, doesn't it?
It really does. It raises that important question. How many other potentially brilliant minds might have been overlooked or even stifled because they didn't conform, because they couldn't thrive inside those rigid structures?
So, okay, no academic jobs, no research positions. What did he do? He took this rather unexpected job at a patent office in Bern, Switzerland.
A patent clerk.
Oh,
Yeah.
Sounds like quite a twist of fate, doesn't it? The future theoretical physicist destined to unlock the secrets of the cosmos, working as a patent clerk, reviewing inventions all day.
While secretly thinking about space and time at night, presumably.
Exactly. It sounds almost mundane, even a bit pedestrian, maybe. But our sources say, and they really emphasize this, and that's where the magic began.
The patent office. On the surface, yeah, it seems like the absolute last place you'd expect groundbreaking theoretical physics to happen.
Right.
But what's truly fascinating here is the unique environment it, maybe accidentally, provided for Einstein's mind. First, and this is really practical but important, it gave him a steady income.
Can't discount that.
Definitely not. Financial security. That meant he had mental space. He was free from the immediate pressures of academic competition, the publish or perish grind.
Didn't have to impress professors anymore.
Exactly. No need to please anyone but himself, intellectually speaking. He wasn't burdened by academic politics or chasing the next grant. He just had time and space to think.
Okay, so stability and freedom from pressure. What else?
Well, second, and maybe even more importantly, think about what he was doing all day. Reviewing countless practical inventions, new electrical circuits, improved ways to synchronize clocks over distances, mechanical devices.
So he was seeing applied physics constantly.
Precisely. He was constantly exposed to applied physics and engineering, seeing how abstract principles actually manifested in concrete mechanisms, in real-world problems.
That must have grounded his thinking somehow.
I think it very likely did. It probably grounded his highly abstract thoughts in practical applications. It might have sparked new ways of thinking about fundamental principles. like reviewing patents on synchronizing clocks. Maybe that directly influenced his thinking about the relativity of simultaneity, a cornerstone of special relativity.
Or electromagnetic devices influencing his thoughts on light.
Could be. He had this unique vantage point, right? Observing the practical workings of light, electromagnetism, mechanics, invention after invention. But crucially, unburdened by academic dogma or the need to follow a specific research program.
It was like an unexpected intellectual incubator.
Perfectly put. It allowed him to connect the practical with the theoretical in a way that maybe traditional academia, with its silos and pressures, might never have allowed. Plus, he had dedicated hours each day for focused, unconstrained thought. That's a luxury many academics, bogged down with teaching and admin, just don't have.
And what an incubator that patent office truly turned out to be. Because just a few years later, in 1905, he's still there, he's 26 years old. Einstein publishes not one, not two, but 4 scientific papers. Papers that would collectively become known as his annus mirabilis, his miracle year.
1905, what a year.
I mean, 4 groundbreaking papers, each one basically capable of redefining a whole field of physics, all from this guy, essentially a lone wolf in a patent office, working mostly in isolation from the established scientific community. It's almost unbelievable. The audacity of it, the sheer impact.
Miracle year genuinely feels like an understatement when you grasp the magnitude of it.
Right.
Stepping back for a second, this single year, it didn't just tweak physics, it redefined multiple foundational fields simultaneously.
Right.
It wasn't just impressive output in terms of quantity, it was a complete and utter reshaping of our understanding of the physical world, period. It speaks to this unparalleled period of intense solitary thought where everything just clicked for him,
Yeah.
synthesized.
Incredible focus.
And the sheer audacity, like you said, and the impact of one individual, largely outside the academic mainstream, producing such monumentally paradigm-shifting work in such a short time, that's precisely why this year is legendary, why it's forever etched in science history. It's a testament to the power of that focused, unburdened intellect.
Okay, so let's unpick these 4 papers a bit. Each one a pillar of modern physics. The first one, for instance. It proved that light can act as both a particle and a wave.
The wave-particle duality of light.
Yeah. It sounds maybe deceptively simple now, but our sources say this single insight laid the very foundation for quantum physics, this whole new field that revolutionized how we see the subatomic world. What was so radical about that?
Well, before Einstein's paper, the scientific consensus was pretty clear. Light is a wave, period. And the wave theory worked beautifully for explaining things like diffraction, how light bends around corners, or interference patterns, like in the double slit experiment.
Okay, so wave theory was working fine.
For many things, yes. But there were these nagging experimental observations, particularly something called the photoelectric effect.
What's that?
That's when light shining on a metal surface causes electrons to be kicked out. And the wave theory just couldn't properly explain how that happened, especially certain details about the energy of those electrons.
Oh, okay. A crack in the theory.
A big one. And Einstein's revolutionary insight in that 1905 paper was to propose that light also consists of these discrete, localized packets of energy. He called them quanta. We now call them photons.
So like little bullets of light.
Particles. Essentially, yes. Acting like particles in this context. This particle and wave duality was incredibly counterintuitive back then. It directly challenged centuries of classical understanding where things were either waves or particles, not both.
Definitely sounds confusing.
It opened up this whole new realm of physics, dealing with the bizarre, non-intuitive behavior of matter and energy at the atomic and subatomic levels, where classical physics just completely breaks down. It was really the first major decisive step into the weird and wonderful world of quantum mechanics, a field that, even today, still messes with our everyday intuition about reality.
And that paper is the one that eventually won him the Nobel Prize, right? Not relativity.
That's right, ironically perhaps.
Yeah.
He won the 1921 Nobel Prize in Physics specifically for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect, so for laying that quantum groundwork.
Wow. Okay, paper number 2 from the miracle year. This one explains something called Brownian motion.
Ah, yes, the dancing pollen grains.
Right, and our sources say this provided definitive proof of the existence of atoms. Which leads me to ask again, wait, people didn't know atoms existed for sure back then. I thought that was like basic science.
It's a really common misconception today, precisely because atoms are so fundamental to how we understand science now. But turn the clock back to the turn of the 20th century, and the existence of atoms was still a genuinely hot topic of debate among very prominent scientists.
Really?
Oh, yeah. I mean, the atomic theory had been around for ages, right? Since the ancient Greeks. And chemists used it as a really convenient model. It helped explain why elements combine in fixed ratios, things like that.
But it was just a model, a useful idea.
For many, yes. There wasn't definitive, irrefutable experimental proof that atoms were actual physical realities, rather than just theoretical constructs or helpful bookkeeping devices. Some very influential physicists were still skeptical.
Okay, so how did Einstein prove it with Brownian motion?
So Brownian motion is that random zigzagging movement you see when you look at tiny particles like pollen grains or dust specks suspended in a fluid or gas under a microscope. This had been observed for decades, named after the botanist Robert Brown. But nobody could fully explain why it happened.
They just jittered around randomly.
Exactly. And what Einstein did, using statistical mechanics, was show mathematically that this erratic movement could be perfectly explained as the result of these larger visible particles being constantly bombarded by much smaller invisible particles, atoms and molecules. He argued and showed quantitatively that the random impacts of these unseen molecules in the fluid were jostling the bigger particles around.
Ah. So the jittering was direct evidence of the invisible molecules hitting them.
Precisely. It was a brilliant piece of theoretical work that connected a visible phenomenon to the unseen atomic scale. It provided that crucial quantitative evidence. It was a profound shift. It moved the atom from being a speculative concept to an experimentally verifiable fact.
Yeah.
It cemented the reality of the molecular world and put atomic theory on an absolutely unshakable empirical footing. Huge for both chemistry and physics.
Okay, so we've got light being weird, particle-wave duality. We've got atoms proven to be real. What's next from 1905?
Next up, the special theory of relativity.
The famous one, declaring that time and space are relative, not fixed, not absolute. For so many of us, myself included, the very idea that time and space aren't these constant, unchanging things for everyone, everywhere, it's still incredibly mind-bending. How did he even get there? It seems like such a radical leap from Newtonian physics.
It absolutely was a radical departure. You have to remember, Newtonian physics had reigned supreme for over 2 centuries. It worked incredibly well for everyday stuff, and Newton's laws assumed that time flowed universally. The same for everyone, everywhere. Tick-tock, same clock. And that space was this fixed, absolute stage where everything happened, independent of who was watching.
Seemed pretty solid. Obvious, even.
Right, it matches our everyday intuition. But Einstein started from 2 seemingly simple yet profoundly revolutionary postulates, or starting assumptions.
What were they?
First, the principle of relativity. The laws of physics are the same for all observers who are not accelerating, regardless of their constant velocity. Makes sense, right? Physics should work the same whether you're standing still or on a smoothly moving train.
Okay, seems reasonable.
Second, the constancy of the speed of light. The speed of light in a vacuum is the same for all observers, no matter how fast the light source is moving, or how fast the observer is moving.
Now that one feels weird. Shouldn't speeds add up? If I'm running towards a flashlight beam, shouldn't I measure its speed as faster?
Intuitively, yes. But experiments were already suggesting light didn't behave that way. Einstein took this constancy as a fundamental principle. And from just those 2 postulates, using pure logic and mathematics, he derived these astounding, completely counterintuitive conclusions. Time can dilate. It can actually slow down for objects moving at very high speeds relative to an observer. Time isn't absolute.
Whoa.
And space can contract. Lengths in the direction of motion get shorter for objects moving at relativistic speeds. Space isn't absolute either.
So my personal experience of time and space literally depends on how fast I'm moving relative to someone else.
Exactly. Your frame of reference matters. It fundamentally changed our understanding of reality, blurring these concepts we thought were totally fixed. It's counterintuitive because we live our lives at speeds that are practically zero compared to the speed of light. We don't directly notice these effects.
But they're real.
Absolutely real. Demonstrably real at the cosmic scale, in particle accelerators, and even crucial for technologies we use every day, like GPS satellites. They have to account for relativistic time dilation to work accurately.
Incredible. Okay, that's 3 papers. There was a 4th in the miracle year.
There was. Perhaps the most famous equation of all time emerged from a short addendum or follow-up paper that year.
E equal MC apart.
E equals MC apart. Energy equals mass times the speed of light squared.
It's on t-shirts, coffee mugs, posters. It's literally everywhere. Our sources make it clear this single, elegant equation would later help explain the power locked inside the atom and, well, change the world forever.
Its universal recognition is just incredible, isn't it?
Yeah.
And for undeniably good reason, because this equation, it's so elegantly simple, but its implications are just profound, earth-shattering, really.
What's the core idea?
It states that mass, energy are fundamentally interchangeable. They're actually different forms of the same underlying thing. You can convert one into the other.
Mass can become energy, and energy can become mass.
Yes. And crucially, it tells us how much energy is equivalent to a certain amount of mass. It implies that a tiny, tiny amount of mass can be converted into an absolutely enormous amount of energy.
Because of the c² part, speed of light squared.
Exactly. The speed of light, c, is a huge number, about 300,000 kilometers per second. So c squared is astronomically large. That means you multiply even a minuscule mass by this gigantic number to get the equivalent energy.
Okay, so tiny mass, huge energy potential.
Precisely. This concept immediately unlocked the understanding of how stars, like our sun, generate their immense energy. Through nuclear fusion, where a tiny fraction of mass is converted into a vast amount of energy, making them shine for billions of years.
And it also applied here on Earth.
And yes, it was the theoretical key, the fundamental principle behind atomic energy here on Earth, both for potentially clean power generation
And for weapons.
and, with tragic irony, for the development of the atomic bomb. What's truly remarkable, and maybe a bit chilling when you think about it, is how such an abstract concept, born from pure theoretical thought in the quiet of that patent office, had such incredibly tangible, world-altering, and indeed devastating real-world applications just a few decades later.
Yeah. It really highlights the immense power and the profound responsibility that comes with truly fundamental scientific discovery.
Absolutely. It's a stark reminder.
Okay, so 1905, the miracle year, launches Einstein onto the scientific stage, even if the world didn't fully grasp it immediately. But his work on relativity wasn't finished, was it?
No, not by a long shot. Special relativity dealt with constant velocity. But what about acceleration? And what about gravity? That was the next big mountain to climb.
And that led to his general theory of relativity.
Exactly. A decade after his Annus Mirabilis, by 1915, he had developed this even more ambitious, more expansive theory, general relativity.
And what truly grabs you here, reading about it, is that this wasn't just like an add-on to special relativity. It was a complete reimagining of gravity itself.
That's the key. A total overhaul.
Not as a force pulling things together, but as the curvature of space and time. I mean, that just sounds like science fiction.
It does, doesn't it? But it was a monumental leap beyond special relativity, and it cemented his place as arguably the most influential physicist since Newton. You see, Newtonian gravity, while incredibly successful for predicting orbits and stuff, described gravity as this mysterious, invisible force acting instantaneously across distances between objects. Like spooky action at a distance.
Which always felt a bit weird conceptually.
It did. Einstein's general relativity offered this radically new geometric interpretation. He proposed that mass and energy actually warp the very fabric of space-time around them.
Like a bowling ball on a trampoline.
That's the classic analogy, yeah. Like a bowling ball placed on a stretched rubber sheet creates a dip, a curve. And other objects, like marbles rolling nearby, follow those curves. So planets don't orbit the sun because the sun is pulling them with a force. They orbit because they're following the straightest possible path through the curved space-time created by the sun's massive presence.
So gravity isn't a force, it's just geometry, the shape of the universe.
In essence, yes. Gravity is a manifestation of the geometry of space-time itself, an incredibly abstract, almost poetic idea.
But how could you even prove something like that? It sounds purely theoretical.
But that's the genius of it. It made specific, testable predictions that differed slightly but crucially from Newton's theory. And one prediction was about light. General relativity predicted that gravity should bend the path of light itself as light travels through curved space-time near a massive object.
Light gets bent by gravity.
Yes, and this abstract theoretical prediction found tangible, observable proof just a few years later, in 1919.
The famous eclipse expedition.
Exactly. During a total solar eclipse, scientists, most notably Sir Arthur Eddington, were able to observe the light from distant stars passing near the sun. And they found that the starlight was bent, deflected from its straight path, precisely as Einstein's theory predicted, and by the exact amount his calculations showed. Much more than Newtonian physics would suggest.
Wow, that must have been a huge moment.
It was enormous. This observational confirmation was so dramatic, so clear, that it propelled Einstein to unprecedented global celebrity, literally overnight. Newspapers around the world ran headlines.
He became an instant icon.
A household name.
Mhm.
Instantly synonymous with genius, a scientific rock star in a way no scientist had ever really been before.
But this fame, this global recognition, our
Yeah.
sources are careful to point out, it didn't really distract him from his core principles. Einstein was deeply committed to his beliefs as a pacifist, as a Jew, as a humanist. It's clear from the sources that his character, his moral compass, was just as significant in its own way as his incredible intellect. And these beliefs really guided his actions in a world that was rapidly becoming more turbulent and dangerous.
Indeed. Those core beliefs weren't just, abstract ideas he talked about. They were deeply held convictions that profoundly shaped his actions, his public statements, his whole life, really. His steadfast pacifism made him an outspoken advocate against war and violence, even when nationalism was rampant, even during wartime. That took courage.
Definitely.
His Jewish identity meant he was acutely aware of prejudice and persecution, especially with the rise of anti-Semitism in Germany and elsewhere. He became a strong voice against it.
And his humanism.
That drove his deep concern for human welfare, for social justice, for ethical responsibility in science and in society. These principles made him more than just a scientific genius. They made him a profound moral voice, a kind of moral compass in a world that desperately needed one.
He used his fame as a platform.
Exactly. Not primarily for personal gain or more accolades, but to champion the causes he believed in, often putting himself at considerable personal and political risk by speaking out. His character really was an extension of his intellect, always striving for truth and justice, both inside and outside the lab.
And those principles, his identity, his outspokenness, they would soon be tested in the most profound and agonizing ways imaginable.
Yeah, the rise of Nazism changed everything.
As the Nazis gained power in Germany, Einstein, who was already a vocal critic of their ideology and policies, and of course being Jewish himself, he recognized the extreme danger immediately.
He saw the writing on the wall very clearly.
He fled Germany, had to abandon his professorship, much of his life there, and he settled in the United States, accepting that prestigious position at the Institute for Advanced Study in Princeton, New Jersey. He stayed there for the rest of his life.
A refuge, but the threat wasn't gone.
No. Even across the Atlantic, the specter of global war and the terrifying potential misuse of scientific discovery, particularly nuclear physics, loomed incredibly large. Which leads us to this really heavy, complex moment in his life. It's 1939, World War II is imminent, and Einstein, fearing that Nazi Germany might be trying to develop atomic weapons based on recent discoveries in nuclear fission.
A terrifying prospect.
He signed a letter. It was drafted mainly by fellow physicists Leo Szilard and Eugene Wigner, who were deeply concerned immigrants themselves, and this letter was addressed directly to President Franklin D. Roosevelt.
The famous Einstein-Szilard letter.
Right. Warning Roosevelt about the possibility of extremely powerful bombs based on nuclear fission, and urging the U.S. to start its own research program before the Nazis could succeed.
Which raises this crucially important ethical question, doesn't it? Especially for Einstein, a committed pacifist.
The ultimate dilemma.
Exactly. Here's a man who abhorred violence, who dedicated his life to understanding the beautiful, elegant order of the universe. Yet he felt compelled to warn the leader of a nation about the potential for a weapon of unimaginable destruction, a weapon based in part on the very principles he himself had discovered with EMCOS.
It must have been agonizing for him.
It had to be. He foresaw the horrific potential of his theories being weaponized, especially in the hands of a regime as monstrous as Nazi Germany. And he felt this profound sense of moral responsibility to act, even if acting meant potentially contributing to the development of a weapon he personally found repugnant.
So his action wasn't about wanting the bomb built.
No, absolutely not. It was about preventing a potentially greater evil, a Nazi atomic bomb. It was a desperate measure, born of profound concern for the fate of humanity, the lesser of two perceived evils at that terrifying moment in history.
It's just such a stark illustration of the heavy burden that groundbreaking science can place on the shoulders of the discoverer.
It really is.
Yes.
Especially when those discoveries have the capacity to alter the course of human history so catastrophically.
And the terrible irony, the tragedy of it all, is that despite his pacifist intentions, despite his urgent desire to prevent a Nazi bomb, Einstein's science would indeed provide the theoretical foundation for the atomic bombs eventually used by the U.S. Our sources are very clear on this distinction, though, and it's important. He had absolutely no part in actually building the bomb.
None whatsoever.
He was the foundational theorist, the intellectual architect of the possibility, you could say, but not the engineer, not part of the Manhattan Project.
Correct. He was considered a security risk, partly because of his pacifist views and background, so he was deliberately excluded from the project.
And he deeply, profoundly regretted the horrific destruction it caused in Hiroshima and Nagasaki.
He did. He spoke out against nuclear weapons proliferation for the rest of his life. He became a passionate advocate for international arms control and world government, believing it was the only way to prevent future nuclear catastrophes. That distinction is absolutely crucial and often gets blurred. Einstein provided the theoretical underpinning. EMC showed how such immense energy release was possible from mass. But he wasn't involved in the engineering, the design, the deployment. His deep regret afterwards underscores the immense moral weight he carried, knowing his pure intellectual quest had inadvertently unlocked such devastating power.
It tells us something really fundamental and humbling about the relationship between pure science and its applications, doesn't it?
It does. And about the often unforeseen, unintended consequences of discovery.
The scientist's responsibility, it seems, extends far beyond the lab.
Into the wider ethical implications of their work, absolutely. It's a sobering reminder that knowledge, while incredibly powerful, is itself morally neutral. Its ultimate impact depends entirely on how humanity chooses to wield it, and that choice often falls far outside the scientist's direct control.
So moving into his later years, after the war, after the bomb, Einstein remained this figure dedicated, first and foremost, it seems, to thought, to peace, and to the continued pursuit of scientific understanding, not to power or political accolades.
Very much so.
Our sources note this remarkable little story. He was actually offered the presidency of Israel in 1952 after the first president died.
That's right, a huge honor.
And he famously, politely, refused. He stated he felt he lacked the natural aptitude for dealing with people in that official capacity and preferred the life of the mind, the life of science.
It's such a powerful testament to his humility, isn't it? And his unwavering dedication to intellectual pursuits over political power or the trappings of celebrity. He truly valued that quiet contemplation of cosmic mysteries above all else.
And during this later period, scientifically, he searched endlessly, quite famously, for what he called a unified field theory.
Yes, his great unfinished quest.
What was the goal there? What was he trying to unify?
It was, in essence, the ultimate scientific dream. He was trying to find a single, elegant mathematical framework, one master equation maybe, that could describe all the fundamental forces of nature as different aspects of a single underlying field or entity.
So bringing gravity and electromagnetism together.
Primarily, yes. At the time, those were the two main forces understood. Later, the strong and weak nuclear forces were discovered, making the task even harder. But Einstein's goal was to show that these seemingly disparate forces were actually just different manifestations of one unified reality. He was searching for that ultimate simplicity and elegance he believed must underlie the universe.
Like finding the ultimate theory of everything.
Pretty much. He spent the last decades of his life on this, pouring immense effort into it, despite the fact that his approach became increasingly isolated from the mainstream of physics, which was heavily focused on the burgeoning and often counterintuitive field of quantum mechanics.
Which he himself helped start, but later had deep reservations about.
Exactly. He famously disliked the probabilistic nature of quantum mechanics, famously saying, "God does not play dice." He felt there must be a deeper, deterministic reality and hoped his unified field theory would reveal it.
But despite his undeniable genius, despite decades of work, he never succeeded in finding that unified theory, did he?
No, he didn't. He never found a formulation that satisfied him or that made testable predictions that could be verified. But his failure in this specific quest doesn't diminish his greatness at all. If anything, I think it highlights the sheer difficulty, the immense challenge and complexity of the problem itself, and the boundless ambition of his intellect to even attempt it.
Yeah, it shows even the greatest minds have limits.
Or perhaps that some scientific frontiers just require more time, new tools, or different approaches. It demonstrates that even for a mind as singularly brilliant as Einstein's, there were scientific peaks that remained unconquered. It showcases the enduring mystery and profound complexity of the cosmos. And it also provides a valuable lesson, I think. Even the greatest minds don't solve every problem they set out to. Sometimes the pursuit itself, the struggle, the questions asked along the way, can be just as valuable as finding the final answer.
And so on April 18th, 1955, Albert Einstein died in Princeton, New Jersey. He was 76 years old. And our sources mention this detail that many people find fascinating and maybe a bit unsettling.
The brain.
The brain. Immediately after his death, his brain was removed for scientific study by the pathologist on duty, Thomas Harvey. Apparently without explicit prior consent from Einstein or his family for that specific action, though Einstein had expressed wishes against elaborate funerals or veneration.
Right. It's a complicated and controversial part of the story.
This act sparked ethical debates that, maybe surprisingly, still continue today. Why the fascination? Why the debate?
Well, the fascination is understandable, I think. It stems from humanity's persistent, almost primal desire to understand the physical basis of extraordinary intellect. We want to know, was there something physically different about Einstein's brain?
Like, could you see the genius in the tissue?
Exactly. Was there a unique cellular structure, a different density of neurons in certain areas, unusual connectivity between regions, something that could explain his profound cognitive abilities, his unique way of seeing the universe?
And the ethical debate.
That comes from the circumstances of the removal, the lack of clear consent for that specific act and preservation, and the subsequent rather strange journey of the brain itself, which Harvey kept for decades, sending pieces to researchers. It raises really important ethical questions about posthumous study, about bodily autonomy even after death, about the balance between scientific curiosity and personal dignity, especially for such a renowned public figure whose body was essentially treated like a scientific specimen.
It forces us to consider the boundaries, right? Where does scientific exploration end and respect for the individual begin?
Precisely. And while some studies have been done on preserved sections of his brain over the years,
Have they found anything definitive?
they've identified some potential anomalies. Things like a larger than average parietal lobe, which is involved in spatial reasoning and mathematical thought, some differences in glial cells. But the definitive link between these subtle physical attributes and his specific world-changing genius, it remains largely elusive, maybe even unknowable. It reminds us, I think, that intellect, consciousness, genius, is far more complex than just the physical structure of the brain tissue itself.
So ultimately, more than his physical brain, more than the tangible form he inhabited, Einstein left behind something far less measurable but infinitely more impactful. Our sources summarize it beautifully, and this feels like the real core takeaway, the true legacy. He left behind a mindset.
Yes, a way of thinking.
One that consistently valued imagination over mere knowledge, fierce curiosity over rigid conformity, and the relentless pursuit of truth over any form of power or easy answers. So what does this all mean for us? For you, listening? For us as learners in our own quests for understanding?
This really is the profound practical wisdom that Einstein's life offers to every learner, to every curious mind out there, that emphasis on imagination over knowledge. It's particularly powerful, I think,
Why is that distinction so important?
because knowledge, while absolutely crucial, is the bedrock, right? Knowledge is fundamentally about what we already know, what's been discovered, cataloged, written down. Imagination, though. Imagination is what allows us to transcend what is known, to conceive of what could be. It's the engine of discovery, of innovation, of all progress, really.
And Einstein's whole life seems to demonstrate that.
Absolutely. His entire life exemplifies how relentless curiosity, even when it leads you to clash with established systems, even when it makes you seem like an outsider, is the ultimate driver of invention. It's the force that truly pushes the boundaries of human understanding. And his unwavering commitment to truth, even when it led him into controversy or exposed uncomfortable realities, it demonstrates the paramount importance of intellectual honesty.
So being a learner isn't just about soaking up facts faster.
No, it's much deeper than that. His life shows us that being a learner is really about how you approach information, how you frame problems, how you engage with the world. It's about questioning assumptions, nurturing your own boundless curiosity, and having the courage to imagine beyond the conventional, beyond what everyone else takes for granted.
So we've taken this deep dive into the life of Albert Einstein, and we've really seen how this extraordinary man who, let's remember, initially struggled with rigid school systems, faced profound rejection early on, went on to completely redefine our understanding of the cosmos: time, space, gravity, energy, matter. And he did this not by conforming, not by fitting in, but by daring to ask the most fundamental, the most unconventional questions.
Yeah.
His journey, from that quiet, curious child to the patent office clerk who single-handedly shook physics to its core in 1905, It's just such a powerful and inspiring reminder. It tells us that true genius isn't always about traditional success or ticking boxes or fitting neatly into those predefined molds.
Right.
It's about cultivating a persistent, relentlessly questioning mindset.
And stepping back, Einstein's life really reminds us that gaining knowledge effectively isn't just about, speed reading facts or memorizing data. It's about learning how to approach problems with that unshakable curiosity, with a profound willingness to challenge deeply held assumptions, even assumptions that seem as solid and obvious as absolute time and space did before him.
It's about developing a way of thinking.
Exactly. A way of thinking that allows you to see connections, to see possibilities where others simply don't, to look at the mundane like a compass and see the profound.
Albert Einstein once famously said something along the lines of, try not to become a man of success, but rather try to become a man of value.
A great quote. Speaks volumes.
And his extraordinary life really teaches us that true genius, true value perhaps, isn't solely about having all the answers. It's often more about having the courage, the insight, the sheer audacity to ask the right questions, often the revolutionary questions. So for you, listening today, what questions are you asking in your own world? In your work, in your learning, in your life? How might you be challenging the fixed ideas, the established ways of thinking around you, just like Einstein challenged the seemingly fixed ideas of time and space?
And this raises, I think, an important final question for all of us. What hidden forces or maybe curvatures in our own understanding, in our own fields, or even just in our daily assumptions are we yet to uncover? What profound insights might we discover simply by embracing that relentless imaginative curiosity that so profoundly defined Albert Einstein?
Until your next deep dive, stay curious.